So, ladies and gentlemen, a very warm welcome to our sixth, I can't believe it's our sixth seminar, the Suman Conversations in Environmental Sustainability, Beyond Greenwashing. Those of you who've been here before, well, first of all, I should introduce myself. I'm Cathy Willis. I'm the principal here. I am a sustainability scientist of sorts, and it's an absolute pleasure to have these seminars going on because the plan, which we originally came up with, is to bring experts, academics, policymakers, all to address, and ask them all to address the same question, so that you really do get a flavour of the different perspectives around a particular question. And each time we have a question, I think, gosh, that's going to be hard to find people to talk to this. And each time we end up with this amazing list of speakers. And those of you who haven't been here before, how we do it is each of them speaks for up to 15 minutes, and I will be waving my folder when it gets to 15 minutes. And then there's time normally for one question, and then they sit down, and then we have the next speaker, and then at the end, they all come up here, and that is the point that we have a panel discussion, very much led by questions that the audience would like to see addressed by the panel. And then at the end of all of that, we can have a drink, and the poor speakers can have more questions thrown at them by you, the audience. Anyway, so without further ado, I will introduce each speaker, and then they'll come up as in the order on the programme. And then, actually, I know all of them have got a slide introducing themselves on the way as well, so I won't waste too much time talking to you. But first of all, we have Madiha Hassan, who was in Oxford, but at the wrong college. I just want to make that point right now. But she is Senior Advisor at Circular Energy. She's a Board Advisor at Hillcore Industrial. She's a Non-Executive Director at Hutan Bio, HiCap, Hygen Energy, and I'm not even going to try and pronounce the last one. So, Madiha, over to you. Thank you very much.
It's an absolute pleasure to be here today. So, you can hear me. I can hear myself. Let's hope that technology works. Here we go. So welcome. Again, a pleasure to be here tonight. Thank you, Cathy, for inviting me. Ray, for all of your hard work in organising this. It's an absolute honour to be here, especially surrounded by students, doctors, professors, and slightly daunting, may I add. But we shall crack on. So a little bit about me. My name is Madiha Hassan, and as Cathy said, I studied maths at Trinity in Oxford many, many years ago. So it's a strange full circle moment to come back and to give a talk here. I graduated and joined PwC in London, qualified as an actuary, so worked in the insurance and banking sector, looking at investment modelling, financial modelling, uncertainty. And then around 2011, pivoted to the energy sector, to oil and gas. I worked with BP for a couple of years in London, and then moved over to the Middle East. Worked with Saudi Aramco, which is the largest oil and gas company in the world, in Saudi Arabia. And then moved over to Abu Dhabi and worked with the ADNOC, the Abu Dhabi National Oil Company. So with these oil companies, I was looking at their investments, developing new projects. And really what stuck with me about the energy industry is how much it was the nexus of geopolitics, of industry, of science, the environment, and capital markets. So when I moved back to the UK 3 years ago, I work now with a number of companies in the energy transition and the climate technology space. I sit on a number of boards, like Cathy said. I sit on a private equity fund investing in green hydrogen, a company that makes biofuels out of algae for sustainable aviation fuels, another company based in Africa that's looking at battery energy storage solutions and solar panels across the continent. So I'm very much in the energy and climate tech space, but from a financial angle, and I hope that's hopefully a different perspective that I can bring to the discussion tonight. So, given my experience, really the question for me is how sustainable and scalable are the emerging energy solutions, and at what costs? Because really for solutions to be sustainable and scalable, they need to have the right type of money and the right amount of money behind them. But it's not just the money and the financial costs, there's many other kind of costs as well. And I hope if there's one thing that I leave you with tonight, it's a sense of how expensive, complex, and nuanced the energy transition is, and how much of an orchestrated approach it requires across countries, industries, and companies. So before I go into some of the costs, I wanted to talk to you about some of the energy trends that we're seeing at the moment, and this is just me talking. There's not many slides, it's more me talking. So what I wanted to do is give a bit of a backdrop of where we are in terms of the energy markets at the moment, what we're seeing in the energy sector, and what's happening to supply and demand. So the good news is we've made huge progress. We know that, we see that. We see solar panels on our roofs, we see wind turbines when we're driving through the motorway. And so here's some facts and figures. In 2012, almost 40% of the UK's electricity was generated from coal. Since then, since October 2024, it's zero. So we've made huge strides in renewable energy generation across the world. We're building renewable sources of energy faster than ever before. However, energy has to keep up with our demands, and our demands are also increasing faster than ever. Faster than clean energy supply is coming online. So here are a few more facts and figures. We all know about electric cars. We see them. I'm sure many of you have them. EV growth in the last 20 years has been explosive. So in Europe alone, new electric car registration has jumped from just 600 in 2010 to 2.4 million in 2023. And there's no sign of it stopping. An EV car requires 6 times more mineral inputs than a conventional car. So lithium production, which we know is needed for electric car batteries, has increased by 300% between 2010 and 2020. The World Bank tells us that demand for minerals such as graphite and cobalt will increase by 500% by 2050, only to meet the demand of these new clean technologies. So our clean future is going to be more materially and energy intensive than ever before. And then, of course, we have AI. And we can't have a talk without talking about AI and technology and the breakneck speed at which AI is developing. City-sized amounts of electricity are needed to train AI models. A recent Wall Street Journal article said that just one data center, devours as much electricity as 100 Walmart stores. The next time you type something into ChatGPT, think about this. An AI search uses 10 times the energy as a Google search. The US Energy Department has stated that while data centers consume less than 2% of US electricity before 2020, they could be using around 12% of all US electricity by 2028. I think the point is clear. Energy demand was already growing, populations were already increasing, our needs were growing, and most of all, we're consuming more than ever. Against this backdrop, we have this exponential surge for energy from AI and technology. And then the question is, who is going to pay for all of this? Where is all of this new energy going to come from? Well, solar panels, wind turbines, we make more of them. What about the infrastructure and the grid connections to connect them to the electricity structure? And we don't think about that. We don't think about actually how outdated our structures and our infrastructures are. So again, the question is, who's going to pay for them? Is it going to be the governments? Well, they don't have the money. The pockets aren't deep enough. So where is this investment going to come from? Well, I think a number of unlikely sources. So we're seeing technology companies like Amazon, Facebook, Microsoft investing in alternative technologies so they can secure power supplies for their data centers. Just this week, a company called X Energy, which is backed by Amazon, closed a 700 million fundraising round to build 150 small modular nuclear reactors in the US and the UK. Yep, you heard that right. Amazon is investing in nuclear reactors. And here's another plot twist. China, which is the largest coal consumer by a significant margin, has single-handedly reduced the cost of solar energy by mass-producing solar panels at a low cost. So the world's largest emitter has enabled the rest of the world to transition to cheap solar power. We have petrostates like Saudi Arabia and the UAE that are building some of the largest renewable energy plants in the world and leading the charge when it comes to carbon capture and energy efficiency technologies. So again, who is going to fund this transition? Most likely, it will be a mix of tech companies, fossil fuel companies, and yes, China. There's the financial aspects of it. What about the non-financial aspects? The unintended consequences. This is a graph that I really wanted to put up here. It's from the International Institute of Sustainable Development, and it was published in 2018. And what it shows is the minerals required for this green energy transition. So we clearly need to build more solar panels, more wind turbines, more batteries. And what it shows is that to do that, we need to mine huge quantities of materials. So the green and the blue dots that you can see across the world are the minerals such as lithium, cobalt, nickel. They're the deposits that we need to meet future demand and their deposit size. So we have lithium in Chile, in Australia, and China dominating the processing of them. We have cobalt in Congo, nickel in Indonesia and Philippines, again, China dominating the processing of them. And then underneath that, you see the shades of the red and the brown. What they are showing on the map are measures of corruption. So a lot of the deposits located in the countries that rank fairly highly, where the deposits are, rank fairly highly in terms of corruption and fragility due to conflicts. And not only that, one more thing. You know those big ecosystems we need to protect and regenerate in order to stabilize the global climate regime? To reset the hydrological cycle and to protect biodiversity, like the Amazon, like the tropical rainforests in Asia, like the freshwater reserves across the globe. You can see, again, they happen to be primarily where those deposits are. So whilst we're charging ahead with renewable energy solutions, the impact on our planet can't go unnoticed. What does changing or eliminating these ecosystems through mining and deforestation do to the security of our planet? Go to the next slide. Don't know what's happened. Am I supposed to? Let's see if this goes. There we go, I think I touched something here. So just to wrap up my talk, really, and parting thoughts, I probably have opened up more questions than I've answered, but what I wanted to convey, really, is the complexity of the climate situation that we're faced with. Are we aware of the true costs? When we talk about a decarbonised future, we're talking about green growth. We're talking about the possibility of decoupling economic growth with greenhouse gas emissions. What we forget is that for that to happen, we need to recouple economic growth with intense mineral extraction. And we can't afford to just shift to a different set of energies, technologies, and materials without paying attention to the unintended consequences. Who's going to finance this transition? Our energy systems have to keep pace with the surge in energy demand. Projects need to be deployed more quickly than ever before, and more capital needs to be directed into the system, and there needs to be much stronger alignment between markets, technologies, and policymakers. And are we prepared to consume less? That's the question we have to ask ourselves. Have we stopped to think that ultimately, to really to help bring about the transition in an achievable way, it's about us consuming less and rethinking our measures of innovation. Because if innovation doesn't reduce our economic footprint within the planetary boundaries, it's not really innovation at all. It's business as usual. That's all I wanted to say for now. I'm looking forward to the discussion at the end of the session, but happy to answer one question. Did you say one question from the audience? Yeah.
Well, thank you very much. You certainly started this evening off very, very provocatively.
Yeah.
Some very interesting questions in there. We've got time for one very quick question. If you want a clarification question, have we got a mic to move around here?
Thank you. Very interesting talk. Can I ask you what you think about the argument that we're actually going down the wrong pathway in battery technology and we should be spending more time developing the green hydrogen economy?
Green hydrogen is incredibly controversial. I know because I sit on the boards of companies that produce green hydrogen. Green hydrogen has gone through a hype. It was the answer to everything 5 years ago, and now it seems to be the answer to almost nothing, and we're going towards electrification. I think the answer is there's a place for both of them. We are going towards electrification of almost everything, as we see, but there are still many parts of industry and transport that can't be fully electrified, and hydrogen has a space. And even if they can, just what I've talked about, the electric system, the electric grid is not going to be able to keep up as fast as the demand for electrification is growing. So there's absolutely a demand and a space for green hydrogen. The company that I work for produces hydrogen double-decker buses. We're going to hydrogen trucks and hydrogen vans, where, for example, electric trucks won't be feasible. When you've got long distances, an HGV driver from London to Scotland that can't keep stopping to charge their electric truck, where they need to just refuel quickly in 15 minutes, have to go up and down, and you've got this 24-hour shifts. There's a space for hydrogen. We've got industries like cement, steel, chemicals that need green hydrogen to decarbonise, and it's the only way. The issue with green hydrogen at the moment is it's being compared to natural gas, or blue hydrogen, which is hydrogen produced from natural gas. And there's such a cost difference that while we might have the production there, and there's a lot of government support, the offtake is not there. We're not being able to stimulate the demand because of the cost difference. And the government's doing a lot to help that, but it's not fast enough. So there's a really slow uptake. So it hasn't become something that you hear about, like you hear about electric cars. So hopefully that answers your question. Yeah.
Fantastic question.
I could go on about hydrogen for a long time. Yeah.
So a huge thank you for starting us so well off today, Matilda. So our next speaker is homegrown. This is Professor Wei Huang, and Wei is a professorial fellow here in college, and he is going to be speaking about artificial photosynthesis for CO2 utilisation. Wei Huang is a professor in bioengineering, so we're now going to hear more about the technology. Wei.
Thank you, Kathy. It's my great pleasure to be invited to give this lecture about CO2, which is my passion. So I will talk about artificial photosynthesis for CO2 utilization. We all be aware, the global CO2 emission is 37.4 billion tons in 2024, and will be increased to 43 billion tons in 2050. To meet 1.5 degree target, we need maximally fixed CO2. I think that's great challenging, 1 to 4 gigatons of CO2 per year by 2050. So I think there's a different approach to do that. Because I'm working on synthetic biology and engineering biology, I would like to discuss if it's possible, we can use a bacteria and a microorganism to fix CO2. So if we think about the sustainable biomanufacturing, if you look at all these organic compounds like sugar, protein, drugs, fine chemicals, if you look at the building blocks, they're just carbon, hydrogen, nitrogen, oxygen. You can get them freely from air. And then the energy source, ultimate energy source would be sunshine. Sunshine would be ultimate energy source, in my belief. And then the only thing is you need a catalyst to stitch these carbon, hydrogen, nitrogen, oxygen together to make different molecules. That would be a sustainable way. So immediately you maybe say that plant can do that for millions of years. So, okay, before we talk about the plant issue, let's look at the energy issue first. If we think about solar energy, if we use solar energy, I think the key issue is harvesting efficiency. So people has calculated that if we can harvest all solar energy to supply the energy to the world, we only need the size like Pennsylvania, the state of Pennsylvania, to support the whole energy demand globally, if we can harvest 100% solar energy. So, however, normally current efficiency is only 1%. That's the challenge. So if you look at this traditional chlorophyll-based photosynthesis, we find there's 4 challenges. One is a narrow harvesting spectrum. The reason you see plants, they are green, because they don't absorb green light. They reflect green light. And also they don't absorb this light. So they only absorb this narrow spectrum. Second thing is, if you have a full sunshine, only 20% can be maximally used, and 80% will be waste, will generate even harmful to the plant. Thirdly, if you have oxygen generation with CO2, we are competing with Rubisco to slow down the Rubisco efficiency. Finally, the chlorophyll-based photosynthesis is so complicated. So far, nobody has ever rebuilt organism to use chlorophyll system from convert a non-chlorophyll system into chlorophyll system. Nobody can do that yet. So we look at nature, we find nature may have some solution. If you look at nature, nature has actually has a two light harvesting system. One is a chlorophyll-based system, reflect the green light. Another is a rhodopsin-based system, absorbed green light. And then you can see they're pink because they only absorb green light. So in that case, the light harvesting is complementary. There's an evolution reason behind that. So later we can discuss if you have interest. That's one point. Second point is chlorophyll system I just mentioned is complicated, but the rhodopsin is very simple. Just one protein pumping proton to generate energy. So actually people recently discovered that more than 50% marine bacteria have a rhodopsin, and they have a reason to have that, to harvest energy, to support their growth. This is a recent survey in Nature. So if you look at these harvesting things, we talk about the light harvesting spectrum. So potentially, Japan has looked at this rhodopsin since 1970. They harvest all different rhodopsin across the world. To search that, you can see they have different colors. That means they can absorb different light spectrum. Another thing is we have AI. Exciting thing is our lab recently, we use AI to design the new rhodopsin, which not exist in nature. That means potentially we can design different rhodopsin absorb different light spectrum. In total, they have a maximal light harvesting efficiency. So this is one point. Second point is 20% full sunshine can be only used. So the solution is solar panel. We have a semi-transparent solar panel, filter out 20%, but 80% can be used to generate electricity. So that potentially, the system can be driven by both light, photon energy, and the electricity energy. So Rubisco, oxygen sensitive issue, is we can separate the two chamber, and then separate that using this proton membrane protein. And this is oxygen. This one has low oxygen, so the efficiency could be higher. We have already used this to make this biodegradable plastic. So finally, complication system. So nature chlorophyll system is complicated. Rhodopsin is simple. But why nature didn't use rhodopsin to fix CO2? So we find out the reason behind that is nature to drive CO2 fixation, you need both ATP and NADH. Basically, it's yin and yang, two things. Only yang is not enough. You need yin and yang. So both proton and electron drive CO2 fixation. That's the complete circle. So in that case, we designed artificial photosynthesis. Okay, keep the story short is, you just look at these two things, ATP and NADH is the main drive to fix CO2. So how to get the electricity? We use a solar panel to drive this electricity, to give the electron to the cell, and they can grow. So that's the point we try to achieve. So now we build the system, use a solar panel, semi-transparent, some energy will generate electricity, and some energy give the photon energy. And the cells were driven by both light and electricity to grow. And of course, because energy input is higher, the efficiency is higher. So in that case, we have improved that gradually. Keep the story short is we have improved step by step. Eventually, we get 45% Faraday efficiency to use electricity, and also driven by light as well. And the overall efficiency is 6 to 10 times higher than current chlorophyll system. So how about large-scale things? So we talk about large-scale things. We have an idea to basically to use electricity in the daylight, use both sunlight and electricity to generate CO2, make a formate. So formate economy, people talk about it for many years, because formate is good energy carrier, can use CO2 as a carbon source to do that. So we have achieved these things. For example, if you look at this solar panel, that's human. That's a huge solar panel, you can do that. And this energy, you can harvest a lot of energy and drive these things. I don't know how to make this movie. Okay, we have already did this small scale, 5-liter scale reactor. And then we can see that with energy, with this solar energy, these cells can grow much better than the cells without light, photon. And the good things, these cells, they can accumulate a lot of white things here. They are biodegradable plastic. We can harvest that to use many different purposes, you can see. So that's that's the idea. So this is a solar panel system in China, Gobi Desert. It's a 400 kilometer long, 5 kilometer width. It's huge. And also you can see that. That's huge. Each one is a solar panel. It's a huge size. They can harvest energy. And then we can use fixed CO2 to make PHA as a product. The PHA can be used for agriculture to make the fertilizer, to make different degradable utility we can use. And this plastic and even clothes, all these things, so can be used. So eventually, my vision is artificial photosynthesis, both based on rhodopsin, can have a sustainable development, only use sunshine and CO2. High efficiency, hopefully 10% efficient harvest solar energy, 6%, 10% energy harvesting. It's simple. It can be, basically we prove that we can use rhodopsin to convert a non-photosynthetic bacteria into fully photosynthetic bacteria. So in theory, it can convert any bacteria into photosynthetic bacteria using rhodopsin system. Finally, it's quite safe. The operation voltage is 1.6 volt. And it's cheap. You don't need metal. It's metal-free electrode. Use paper cloth, carbon cloth. Finally, it could be designable. Use AI to improve that. Finally, I thank my team and founding body. Thank you very much.
So thank you. Another fantastic, really, really interesting talk. Let's have some questions. We've got time for one question related to that, if anyone wants a clarification question in here. There's one at the back.
So what are the challenges? What are the challenges? Like you gave the positive side.
The challenging?
Yeah.
Okay. I think the challenging is implement that. Actually, some people commercial people has already contact with us. At the moment, by the way, because UK has a large ocean area. So like Thailand already discussed how to deploy these solar panel on the ocean. So you don't need too much area, and you can fix CO2. So we can discuss the details later if you like. So we do have this plan, and we are going to implement that soon. At the moment, we can produce a large amount of PHA, which is biodegradable plastic. That's what we can do now.
Okay. Thank you very much. I'm sure we're going to have a really interesting discussion at the end. Thank you very much, Wayne. So our next speaker is another Teddy Hall alum, actually alum this time, and it's Dr. John Waite. John was engineering fellow here, left in 2000.
Material science.
Oh dear, I always muddle those up. Okay, apologies already. And he now is the CEO of a spin-out that you created yourself.
Not a spin-out even, yeah, okay. I can go straight to the introduction if you want.
I'm going to be quiet right now. Over to you.
Not a problem. So, yes, I'm here to present my company, FICO Bloom, and then some general thoughts about the space. I'm going to start with my journey since I left Teddy. I think this is why I was invited back to do this. Is not because of my PhD, not because of all my thought-leading podcasts that I've done. I've done one podcast. But because of the company that me and my co-founder have built. And then I'm going to talk a little bit about the title of this topic, which is sustainability and scalability. What does that actually mean to someone like me, who's maybe an early stage technologist, or maybe in some academics that are out in the audience thinking about how they can commercialize something. And then finally we're going to talk. Medea nearly touched on this, but green premiums. What does it actually mean, and how can we actually affect this as consumers and as people interested in the climate? So to start with, I joined the Hall in 2011. I was here many, many years ago. I did material science as an undergraduate. I'm here with my undergraduate cohort as we graduated in 2015. And I loved it. I couldn't get enough, and I stayed on. what a choice. And I stayed on to a DPhil in nuclear materials, focusing on fusion energy. See a picture of me there at the Teddy Talks in the principal's lodgings about, I think, 2018, 2019, some kind of time. And when I finished that, I realized that although I really love sustainability and I really love material science and I really love nuclear, I was not cut out for lab work. I never wanted to work in a lab again. Whatever job I did, no more lab work for me. And I was sort of encouraged to apply for this program called Entrepreneur First, now rebranded to Entrepreneurs First. And that was, it's basically Love Island meets Dragon's Den. It's the only way I can explain it. You're meant to go with no idea of what you're going to do. You're just someone who might start a company, and they basically pay for you to move to London and network aggressively. There's 100 people all in your cohort, and you just chat, come up with ideas, test ideas. If it's a good idea, you pitch them. That's the Dragon's Den bit. And if they like it, they might invest. And if it's a bad idea, they tell you to break up. You're no longer in a partner. Find a different person to work with. Find a new idea to test. That's the Love Island bit. I was very fortunate. I found this guy called Ian, who's an incredible biotechnologist, really smart guy. And most importantly, he had the one thing that Entrepreneur First really, really needed, which was an idea, and I had no ideas at all, so I joined him. He's the brains behind the operation. He's my CTO. I sometimes say he's the brains, I'm the mouth. I do all the talking, the pitching, the commercials, the operational side of the business. So that's a bit about me. Now, what does Fico Bloom do, the actual truth of it? So they've mentioned a bit earlier, biofuels. Well, biofuels are there to displace fossil fuels, but we try to make the best possible biofuels. We're here to displace bad biofuels as well as good ones. The thing about biofuels, as Wei touched on, is they use the power of photosynthesis to turn CO2 in the atmosphere and sunlight into oil that you can burn. When you burn it, it just goes back in the atmosphere. That's fine. It's carbon neutral in theory. The problem is if skipped ahead a bit. If you're making your biofuel out of palm oil, you've had to level a rainforest just to grow it. It's not very sustainable. The actual carbon impact of a lot of biofuels is barely any better than fossil fuels. You might as well not bother. So what we did is we turned to algae. Again, already mentioned in this thing. Algae are photosynthetic monsters. They are 10 times better than any other living creature at sucking up CO2, sucking up sunlight, and turning it into something. And these allow us to grow biofuels without sort of disturbing agricultural land, disturbing rainforests, and they offer us a pathway to really, really good biofuels. And that's why we're so passionate about it. Okay. The bad thing is, algae do not want to give us their oil. They are awkward little critters. And so the only way to get oil out of algae is to, firstly, you take a big pond full of them, and you have to kill them. You have to drain all that water away, and they have to dry this like sludge into a completely dry powder using a centrifuge. It's so expensive. You then have to break the cell walls down. You have to extract the lipids with a solvent, get rid of the solvent, and all you're left with is a pile of dead algae and some oil. Now, that's not very efficient. My analogy for this that sometimes works is that it's like a farmer who every year they buy a load of really big equipment and they chop down their orchard and they take the apples off of these dead trees and they turn around and they replant the orchard. It's very inefficient, it's very costly, and it doesn't really work. And previous companies who've tried to do this have failed. So Ian's idea, again, can't claim credit for this, was to use genetic engineering to change the way algae behave. Instead of hoarding their oils, what we do is we engineer them to directly secrete it continuously. And this means instead of having to harvest that biomass and do all that work, we just scoop it off the top. We just come in, we actually use a sieve. It's very low tech. Just use a sieve, you get the oil out, leave the algae alone. You can come back day after day after day after day. No equipment, no downstream processing. So it massively reduces the costs. That's the idea. Of course, that's obviously easier said than done. We're still working on the actual technology to do that. But how it would work in theory is we would own these big ponds. These are some aquaculture ponds that exist, I think, in the US, maybe in Hawaii. And they grow fish. So you can use something very similar to grow algae. So imagine these, really green, full of algae. What we do is we collect that oil off the surface. And this is where it gets a little bit more complicated, because that oil is not crude oil. It's much more like a vegetable oil. You can actually cook with algae oil if you really want to. It's quite good for you, actually, apparently. So what we have to do then is give it to a customer. That customer is actually the BPs, the Chevrons of this world, that convert it from a vegetable oil into something that looks almost identical to kerosene or biodiesel or diesel. And so there is still a place for the oil companies in this world. You know, we have no funders who are oil companies, but we're probably not going to avoid it for much longer. And then after they've done their business, they then sell it off to airlines or things like that. So there's a big supply chain that we as biotechnologists fit into. You know, we're not in isolation. We don't just develop this technology and then move on with it. It's all part of a bigger thing. So a bit on my journey. So when we first got funding, we did not get a lot of funding. You know, Entrepreneur First, they fund a lot of small companies, small tickets everywhere. It wasn't a lot. And so we couldn't set up a big lab and hire a load of people. We actually rented 1/4 of a shipping container. That was our first lab. We were in there for a couple of years. It really was not glamorous. When it rained, I was still on the picnic table outside in the rain. Wasn't great. So this is a picture of our shipping container. We don't forget where we come from, but we worked very hard. We proved what we need to do, and we managed to then raise a much bigger round. We've expanded. This is our lab now. Still a bit shipping container chic. The roof of our lab is the A40 flyover in London. If ever you're driving into London, you are going directly across our lab. But we have about 13 people all working on genetic engineering scale-up, which we are about to start next year, which is really exciting. We're going to go from the lab where we have test tubes of algae to where we have foot baths of algae. It's a slow process, you know, we're working on it. Okay, deep breath. That's the phycobloom bit. Now we're going to take a bit of a step back and look at sort of a bigger perspective. What does it actually mean to be sustainable and scalable? Because I talk to a lot of startups, talk to a lot of investors that I think do not understand this at all, and I think it's worth sort of taking a beat and actually thinking about these ideas. So what makes it sustainable? And we're going to sort of talk about it in general and then think about the SAF case, sustainable aviation fuel case, and sort of assess them. So the first thing you have to ask yourself is how many greenhouse gases, CO2 or others, will your technology that you're trying to commercialize actually create? For biofuels, it's pretty obvious. You are burning things into the air. But even if you're producing something like hydrogen, there are going to be emissions related to your process. You have to assess that. Secondly, what do you displace? Do you displace a dirty industry or not? Because I've spoken to people who have a technology, it's really cool, but they don't displace anything. So it's clean, but it's not removing any emissions. You're not stopping anything happening. You're just a cool technology. Great, that's perfect, but what else? And then finally, the really hard one, what second order changes do you need to actually make this work? What else has to be true that's outside of your control for this to work? Like, we produce oil, but we need all those chemical plants to make sense. We need them to work. We need them to be sustainable as well. It's not good enough just for us to do our job and then stop. So when it comes to SAF, this is a really important point. You'll hear a lot about SAFs, and the UK is about to have a really big push in driving up SAFs. But if your SAF is not made from a good quality feedstock, if it's made from palm oil, it is not sustainable. The S is not load-bearing. And so you have to have a really reliable, high-quality, traceable feedstock, which I think is going to become much more topical in the future. What greenhouse gases does it displace? Really easy for SAF because you're literally displacing part of the fossil fuel barrel. It's you know, for every drop of SAF you use, you're using one fewer drop of kerosene, so that's great. And then finally, the second order effects, there's quite a bit for SAF. You need a whole new supply chain, a whole new industry of chemical plants to convert your vegetable oils into fuel. So that's a huge amount of work to be done. So overall, SAF's pretty sustainable. Scalable. I'm not quite sure. I've got a bit of time left yet. 5 minutes, perfect. So what makes a solution scalable? Well, firstly, what you have to ask yourself is what global limits actually exist? If you want to operate at scale, what's going to say, right, you can't build any more facilities or you can't operate there? For us, it's land. We need to grow ponds, so we need land to grow ponds on. That's one of our limiting factors. Number 2, how do you prove your commercial value? What's the pathway to do that, and how are you going to keep all your partners happy? Now, for something like an electric car, that was actually a bit of a stumbling block, because you can build an electric car. There were electric cars 100 years ago, but you need, for your customers, you need to have a whole infrastructure behind that they can guarantee there's a charging point. And so for a lot of technologies, it actually only makes sense once you're at the billion-litre scale. So how are you going to tread that path all the way up? That's a big question about scalability. And then finally, competitors. People don't like talking about this. Startup people really don't like talking about it, but there's never only one solution. There's the dirty fossil solution, and then there's other clean tech solutions. And you might not have the winning idea. It might be a really, really good idea, but it might be the second best idea. So does it still make sense in that context? For SAFs, again, global limits, it's the supply chain. There probably isn't enough feedstock available for all biofuels that we want to consume. If you look at the road travel, you look at aviation, and you look at shipping, it's probably not enough capacity to make biofuels for all of them. We're going to have to make tough choices about how many flights we take in a fully sustainable world. In terms of for SAF, the pathway is actually really easy. You literally blend it with kerosene. So you take half a barrel of kerosene, half a barrel of SAF, just mix them together. Really easy to deploy in partials. And then finally, competitor technologies. I would say within the SAF space, there's not really any reasonable competitor. Hydrogen, there was a bit of a push on hydrogen, but in order to commercialize hydrogen, you don't just need new planes. You need new fueling terminals, you need new airports, you need new routes, you need new everything. So that's going to take 50 to 100 years to scale up. And then batteries, again, this is a competitor piece. Electric aviation is really cool, but electric planes are going to be small and they're going to be short distance. Are you really competing with planes, or are you competing on train tickets for billionaires? And I think a lot of those eVTOL startups we've seen, they're doing very short journeys for very rich people between very nearby cities. That's really what they're competing for. So again, very important. And then finally, This is not standing still. This is a moving target. These timelines are 20, 30, 40 years. You need to, as a technologist, assess these things. How are they going to change? When someone's going to have some new great idea that's going to completely change it. So everything I've just said might be completely untrue tomorrow because someone's going to solve a problem. I have not heard of waste technology, and it's really interesting. I'm going to pick his brains tonight. You know, you have to stay live, you have to stay current. So for the challenge for investors and governments that I think Linda might talk about is, how do you predict what's going to happen? It's almost impossible. So finally, just had this big discussion about a holistic way of assessing a technology to tell whether it's sustainable, scalable. But at the end of the day, that doesn't matter. People who make choices, they don't make choices based on the sustainability and scalability of technologies. They base it on price, and that is where it all comes down to. Green premium. This was a term, I think, coined by Bill Gates, and it's the difference in cost between the clean alternative and the current sort of fossil technology. It's how much extra the clean thing costs. And ideally, you want that to be zero or negative. Now, Tesla's more recent strategic choices have been odd, but in the early days, 10, 15 years ago, they actually had a really good idea, which was targeting the luxury segment, people that would happily pay a huge green premium, making a really luxurious car that people would pay a premium for, and then scaling up within that and getting cheaper and cheaper and cheaper and cheaper and cheaper until they had sort of a mass market technology. That's a really good idea. It also doesn't really apply to a lot of clean tech. If you're trying to produce a commodity chemical, there is no luxury market for oil. There is no luxury market, really, for hydrogen. So what do you do? And also, what do you do if, you know, electric cars are great because there is a pathway for them to be cheaper than fossil? There's not a way to be cheaper for fossil for a lot of different technologies, so how do you do that? SAF's one such example. It will always be cheaper to dig oil out of the ground than it will be to grow it from a plant. And so what we have is government policies, UK, US, EU, China, have mandated legislation guaranteeing the SAF market will exist, guaranteeing it will be there regardless of cost. So those green premiums are actually baked in. You cannot avoid them. Hydrogen, already been mentioned a couple of times, but it's worth saying there is a hydrogen market. There is 100 million tons of hydrogen consumed every year in this world, primarily to make fertilizers. If you want to make that from fossil hydrogen to green hydrogen, it's going to roughly double the cost of fertilizers. Farmers will not pay that green premium. The agricultural system we have cannot tolerate it, and so it is not taken up. So this is a place where that green premium is a killer for the hydrogen industry. Final slide, I promise. Final thing, two things that really get my goat when I'm talking to people. We've been spoiled with microprocessors and solar panels with costs coming down. Costs really do come down. Theodore Wright noticed this in his aviation plant. As more components were made, costs came down. That is at the end of it. But a lot of things don't come down like that. A lot of clean tech relies on really basic things like steel, cement, pipes, pressure vessels. The human race has made billions of these. We're not going to be making that many more. We're not going to be finding improvements in some of that stuff. So you have to think with your clean technology, what elements are actually going to be cheaper? And I think, again, go back to the hydrogen, that's where hydrogen's had a bit of a stumbling block. There's a lot of very standard components in a hydrogen plant that aren't going to become any cheaper. Nuclear, where I started off, has become more expensive over time, even though there's been actually a lot of innovation in the nuclear space. And that's, again, there's no learning curves there. And then finally, the circular economy. I think this is sometimes a bit of a misnomer. Circular economy is really dangerous. It's also very fashionable within the biospace that I work in. A lot of people find like some kind of waste resource, something that at the moment is like incinerated, and they're like, oh, I can turn this into a biopolymer or into some kind of weird fuel thing. That's really, really good. But if it's a waste, that is a fixed supply. There is only so much waste being produced every year. And as soon as you say, right, I've got a function for this waste, I'm going to do something with it, it's not a waste anymore. You've got to pay for it. And you've maybe just created demand, so that price is going to spike. Perfect example here is used cooking oil. So most biofuels that you go in, all the SAF that's going to be produced this year for the aviation sector in the UK comes from used cooking oil. Right now, used cooking oil is more expensive than virgin cooking oil because it's more valuable than that. So in Indonesia, they are sending us shipments of used cooking oil that is actually virgin palm oil because it's more valuable. So that's it's not a bad thing. This is a good thing. We've generated this new technology. We found this new way to do it. But that's the consequence of having a fixed supply and unlimited demand, you know. So be very, very cautious about utilizing wastes. So finally, my summary slide. What are we doing at Ficobloom? We're using synthetic biology, genetic engineering to reduce the cost of biofuel, making the most sustainable biofuel the most scalable as well. If you want to determine what is sustainable and scalable now and in 2050, it's really not easy. Take your time, have a real look at the different trends. You're going to have to speak to a lot of people, read a lot of papers. And then finally, regardless of how good a technology is, Price is what matters. Innovation is really, really important, but it's only part of the story. There's also policy, there's also consumer pressure, there's also regulation that really affects price and really changes it. Thank you very much.
So thank you for another excellent brief overview of this technology. I've learnt more in the last 45 minutes than I've learnt in a long time on all of these things. Can I just actually ask one question? How much does it cost to convert your FICO Bloom oil into sustainable aviation fuel? Is that I'm just thinking about your last point, and actually what's the cost in there?
Yeah, it's a good question. So the cost of conversion is not actually that high. So we feed into what's called the HEFA process, hydrotreated esters and fatty acids. That's already well at scale. It already exists. It's pretty cheap. I think it's about $1 or $2 a gallon. It's marginal. The cost of our feedstock, if you factor everything in, like the capital of building these ponds and running them, it comes to about $1,000 a ton. I'm switching between units here, but kerosene is about $600 a ton, so it's a markup on that.
Yeah.
Or that $1,000 a ton is our projected pathway at least. It's a lot more now when we're in a bathtub. But yeah, it's still going to be more expensive, maybe double the cost of fossil.
Okay, thank you. Have we got time? We've got time for one more question from the audience. If not, we will move on to our... Oh, there's one right at the back here. This is a quick question.
Hello, I wanted to ask about the land use issue of the ponds and of the scalability, if you can speak a little bit about that.
Yeah, of course, and it's the first question with biofuels, as it rightly should be. The reason to use algae is the land use. That is their main advantage. They are, as I said, 10 times or more efficient photosynthetically and in terms of land than any other crop. So you need a lot less. Also, the land you need is not... You don't grow them in soil, you grow them in water. So actually you just dig a trench in a desert, you find a brownfield site that you don't need, and that's where you put it. So there's actually lots and lots of land. If you look at how much land it's going to take globally, if you use our technology, it's about 77,000 square kilometers of land you need to give over to algae growing to displace all of aviation, which is a lot. But right now as a planet, we use about 600,000 square kilometers to grow food crops that are then turned into fuel. So it's actually a reduction of what we already do, and we're shifting away from farmland. So the land use for algae is the reason to go there.
Yeah. We'll have other questions when we get to the panel stage. Brilliant. Thank you very much.
Thank you very much.
Very thought-provoking talk. And we're now moving on to our last speaker. Thank you. And this is Professor Tina Fawcett, who's an Associate Professor at the Environmental Change Institute. And so I'm just going to hand over to you.
Right. Well, good evening, everybody. So I'm at the Environmental Change Institute, and most of my research is around energy demand and energy policy, and so that's the perspective I'm going to be speaking from. And hopefully I'll pick up a few points that sort of connect with the other speakers as well as I go along. So I'll be sort of slightly looking at my notes to see if I can make a few connections. I thought I would start with this and a bit of audience participation. How many people have seen this diagram before? So I would say that's probably a minority of people, or certainly less than half. So this is called the climate stripes, and it's an infographic about temperature change. And this is for Oxford, and each stripe represents a year. And what the colours tell you is how warmer or colder it is than the average between 1960 and I think 2000. And obviously blue is colder and red is warmer, and I think you can probably guess which way the chart runs. So this is, at this end, this is 1825, and I think this is up to 2023 here. So, I mean, we know this, right? And the reason Oxford's got such a long climate stripes is because of our Met station, now incorporated as part of Green Templeton College. But we have to remember this context. I'm sure we're aware of it, but we need to remember it. And what is this climate change mostly driven by? Most of it comes from fossil fuel burning, carbon dioxide, as the other speakers clearly talked about. And as we also know, things are not yet going in the right direction. Like carbon emissions from fossil fuel burning are still going up. There was some good news recently that people were thinking perhaps China has kind of peaked its carbon emissions from fossil fuels, and let's hope that's true. But there's a huge amount still to do. However, there are also sources of hope. So I wanted to sort of point out how the UK has been doing. So there's 2 lines on these graphs. So these figures are from the UK Climate Change Commission, which is the body that advises government on how it's going to meet its carbon targets, and particularly how it's going to get to net zero by 2050. And so up here we've got millions of tons of carbon dioxide equivalent, and across the bottom we've got time. So it starts in 1990 and it goes to 2023, I think, or 2024 possibly for the top line. And the top line is the territorial emissions, so the greenhouse gas emissions that the UK generates within its borders that we use, so it minus exports. And the yellow, and so that's halved since 1990, right? Our economy's grown, there's more of us, and our greenhouse gas emissions, that's carbon emissions from fossil fuel burning, is the majority, but there's also methane emissions and other emissions from agriculture and other processes in there. So that's a really good news story. And when you tell people that, they often say, yes, but what about what we import from other countries? And that's what this yellow line is. And this is telling you what the UK imports in embodied carbon and greenhouse gas emissions, essentially in the stuff that we buy. So that number has gone up a bit, but still the total of the two is still a downward trend. And that's really important to think, actually, we know something about how to make progress here. We've not gone as far as we should have done. If we think about, all the reasons to be worried about what's happening to the climate and what's happening to nature, but we know we can make progress. So how have we done it? Well, obviously I'm simplifying, but you think about it in 4 things. If we go back now away from all greenhouse gases and just go back to the energy systems and fossil fuel emissions and burning, approximately, in this order, the 4 things that have happened is we've increased energy efficiency, leading to reduced energy use. So the UK economy is actually using less energy now than it was in 1990, and the population's almost 20% higher, and GDP, I should have looked up the figures, I didn't, obviously higher. So that's important to see that we can do that. We've decarbonised electricity, and that's already been alluded to by the other speakers. So carbon emissions, 80% lower in 2024 than they were in 1990. Last coal-fired power station shut down end of last year. And the UK government's target at the moment is to be 95% emissions-free by 2030. And they might not quite make that target, but they're giving it a good try. We're beginning to electrify energy end uses, and we've had some structural change in the economy. So we've got a less big industrial sector than we used to. So I'm not saying these are all positives in all the way around. And obviously, these factors, integrate with each other. If you're using less energy, it's easier to meet your energy demands through renewables. If you're electrifying your energy end uses, you're also making them more efficient. So there's a lot of sort of connections between these factors. And I suppose if we're thinking about sustainability and scale, well, obviously, the energy you don't use, that's pretty sustainable. That's a really good strategy for becoming more sustainable, is to find out where you can use less energy. And one of the key ways, this is an example of product policy, right? How are we using less energy? The humble fridge is a really big success story across Europe. I'm using the UK figures here, but you'd see the same across the whole of Europe. In about 1995, which is here, so I'll just explain so this is total energy use for all fridges and freezers in the UK. This is 1980, and it goes up to 2023. These are modelled numbers, but they're based on very good data. And what it shows you is energy use for all appliances was going up a bit till about 1992 or 3. Policy came in here, and from that point onwards, a selection of policies including information for consumers and minimum efficiency standards, energy use has gone down. And it has dropped by 60% since 1995. That's massive. Fridges and freezers are one of the most commonly owned appliances across the world, and actually they're also pretty commonly regulated. So it's a sort of system we understand, and we understand how to make it work. I won't dwell on this. This is just a sort of visual representation of how policy has changed across the EU, and the UK has kept using the same mechanisms even though we've now left the EU. And it's to do with enabling consumers to see the difference between efficient and inefficient things, persuading manufacturers to compete on efficiency, and bringing in minimum standards and not allowing people to sell less efficient products over time. And that's a story we've seen in a lot of areas. And it's, I would say this kind of policy it's scalable. I mean, this kind of policy happens across the world. Something like 80% of all fridges are regulated using these sort of policy tools. And it's sustainable because we're enabling people to get what they want using less energy. So sometimes it's not that big and clever to make quite big, to make quite big improvements. But, okay, so that's where we've got to. So what else have we got to do? Again, these are figures from the UK's Climate Change Committee, and they're looking forward to 2050, by which time the government has said we'll be at net zero, and saying, okay, so what are our major challenge areas? And I won't go through all the details on this graph, but I'll just point out a couple of things. So this yellow one that goes down to almost zero, close to 2030, that's electricity. So it's saying, yes, we can decarbonise our electricity. The two top things here at the moment are surface transport, so mostly cars, and residential buildings. And they're expected to make huge changes. The carbon emissions from those sectors have got to reduce a lot if we're going to meet our targets. And then we've got, which we've just been talking about, aviation. And aviation, the emissions are expected to go down a bit, but not all that much. So aviation and agriculture are the areas where we're going to need to do some form of carbon capture if we're really going to get to net zero. I think, so just to come back to this question of scalability, so I've been sort of promoting the idea of actually energy efficiency has been important, is still important. And we're doing pretty well on electrification, renewable electricity, which is great. And just to sort of, what sorts of technologies do we need to get us where we're going to? So we've heard examples, already about particular technologies. And this is just a bit of work by one of my colleagues, Charlie Wilson, with some other people looking at one way of trying to understand innovation and learning curves, which we also already heard about, is thinking about how scalable are technologies. And essentially their finding, based on empirical data, was that more granular energy technologies, so that means things that are smaller in scale, physical scale, and also cheaper, scale faster, and that you learn faster and they can take up the market faster. So these are quite complicated sets of diagrams, so I'm not going to go through all of it, but this one says diffusion time scales, and this scale up here tells you the number of years it takes you to get from 1% to 50% of the market for any particular product. And across here is unit cost in US dollars, and so that's going up and that's going up. And what that's telling you is, in general, the more expensive something is to build, the longer it will take for that technology to capture 50% of the market. And then they have these two sort of learning curves, which we've already heard about. And just to point, they're sort of done on different bases, but just to point out one thing here. So these are all individual technologies that they've got data from, and they're basically finding out the bigger it is, the slower the learning curve. And these ones that have got negative learning curves, one of those is nuclear, which we've already heard about. Yeah, so I'm not sure about 150 small modular nuclear reactors, if I'm honest, but we'll find out, won't we? So that might tell us something about the sorts of technologies that we need. And in a way, so just to go back a bit, in a way that's a good thing, because if we think about the key technologies for the UK, for homes and for transport, those are cars, and they're probably air source heat pumps, and those are modular, those are scalable, they're less impactful than what they're replacing. So that's good news, actually. But while technology can bring us solutions, it can also bring us problems, of course. And one of the problems, so electric vehicles, okay, they're very good. They produce a lot less carbon and greenhouse gas emissions than fossil-fueled ones. But unfortunately, as with normal sort of petrol vehicles, we're buying bigger and bigger EVs. So this is a sort of quote from the International Energy Agency. And they're basically saying, because we're building bigger and heavier electric SUVs, it's kind of nullified the improvements in energy consumption and emissions achieved elsewhere in the world's car passenger fleet. So that's all SUVs, not just e-SUVs. But the point is, you know, if we're not careful about over-consuming things, these advantages that we're hoping for won't arise. Now, it didn't happen with fridges. When fridge sort of regulations came in, people were saying, well, you know, if they're more efficient, everybody will just buy much bigger fridges and you won't get any energy savings. That has turned out not to be true, fortunately. Right? People don't want that much bigger fridges. But it hasn't turned out to be true for cars. And we've got to think, well, what are we going to do about that? We don't need new technology for that, but we do need new policy, a new social agreement about what's okay. Fine, before I close, I'm just going to do a quick advert. One of the jobs I do is I'm the convener of the Oxford Energy Network, which runs sort of term time seminars and annual events. And so if you're interested in finding out more about all these aspects of energy, please do connect with us. Right, slightly cheeky. Right, let's just move on. So my sort of concluding thoughts are, I think for the UK and Europe, by 2050, we could definitely meet, or we could get close to net zero, with technologies that we've already got that are already deployed at scale, possibly apart from carbon capture and storage, because I know it's kind of hard to agree that that's deployed at scale at the moment. But you know, that's not saying we don't need innovation. I mean, of course, everybody wants new and improved technologies, and it can make the route to net zero a lot more affordable. It can make it more less environmentally damaging as we get these new ways of sort of delivering what people really need. And you also might be thinking about energy security and energy justice, not just environmental improvements in the energy system. So these new technologies, of course, they're vital. I'm not saying that they are not, but so too is implementing existing systems and existing solutions. Let's not forget about those. And let's also think about restricting energy-hungry and high emissions products, because if we're not doing that, then we're not being serious about getting to net zero. Technology is really important, but it's just one element. I've focused on it here, but of course, technology is embedded in socio-technical economic systems, all of which are very complicated. And we know it's not just a technology story, but it's understanding technology's part in all of this is what we've got to do. And I think, you know, it's clear that, I think all of the speakers have talked about the role of technology and some of the innovations policy and some of the innovations they're looking at. So I think it's clear that we do need evidence-based long-term policy to guide us towards this just transition. Thank you.
So thank you for another really excellent 15 minutes on this whole topic. We've got time for one question, and I'm going to ask all the speakers to come up. We have a question here.
Thank you so much. I was wondering, do you think net zero can be achieved without the use of SMR or general nuclear technology?
Well, SMR is kind of is that a technology at the moment? It's a sort of an intention, isn't it? To some extent. Obviously we've got conventional nuclear power. I think, what I would say is there are scenarios that people have created that show how you can reach net zero without using it. So views differ. But there are, I think, plausible scenarios where people have shown by using sort of wind, solar, hydro and other renewables that you don't actually need nuclear. And there's actually quite a good argument that nuclear is not actually a very good partner when you've got all these kind of renewable sources on your system. Nuclear that needs to be always on is actually not really what you need to help you balance your electricity system as everything moves to electrification. So I think there's quite a lot of, apart from the costs, apart from the concerns about its environmental impact, I think there's quite a lot of questions about whether nuclear really will be an important part of a future electricity system. But it's not my area of expertise, but that's where I would be with that.
Okay, thank you very much. Actually, I do have one quick question. I'm amazed about the fridges.
Which is amazing.
Is there anything else that's like the fridge that has got that sort of good news aspect to it?
Lighting.
Lighting.
Yeah, lighting's just as, it's sort of 10 times more efficient than it was 25 years ago. I mean, we're using more of it. We're lighting up things that we didn't used to light up.
Yes.
So there's a bit of a take back, but nevertheless, lighting also uses an awful lot less energy than it did. Washing machines are better, tumble dryers are better. I mean, there's quite a lot of air conditioners could be a lot better, and that's massively important, obviously, for particularly hotter countries. So.
I mean, I just think it was quite those graphs showing actually it's the smaller appliances can make a big difference. You suddenly think about scalability, and it somehow becomes much more manageable in the way we view it. Right, I'm sure you all have many questions. I would like the 4 speakers to bring their chairs up here. And while you're all thinking of your questions, there's a few rules about the questions. I very much hope you all, you can ask either for the entire panel or for individuals. When you ask your question, please could you state your name and your affiliation? And also, please could you keep your question very brief, because we really want to hear from the speakers and not necessarily have another lecture going on in the room. But you all know that. Okay, I'm just going to start by asking a question actually for all of the speakers, just to get us going. The thing we haven't talked about is energy storage. And how do we store the energy that's created by these different systems, or can we? I mean, I'm thinking about electricity from wind power. Is that a barrier, and are we getting in the right place for that? Maybe you could just address that.
Well, we've got a lot of actually energy storage experts in the room at the moment, so I kind of almost feel I should hand over to them. I think where the biggest challenge for electricity storage really is seasonal storage, because obviously a lot of, certainly in Britain we use a lot more energy in winter than we do in summer, and in other countries it might be the other way around. And so we're pretty good on seconds, hours, and even days. And sort of battery capacity is being built up all the time, and there's really interesting options around with all our electric vehicles if we can start using them as batteries as well. So I think that there's a lot of, that should be okay, but it's this kind of longer term seasonal storage that people are really kind of needing to look into.
Yeah, and does the whole question of energy storage and the cost of that come into your economic application?
Yeah, absolutely. So as part of the electrification angle and renewable sources, battery energy storage is huge at the moment. There's a lot of policy around it as well. There's limitations currently around batteries. Again, I'm not a battery expert, so if there are battery experts in the audience, happy to hear from them. But in terms of the hours that they can store, there's limitations. Actually, I think the maximum is, for the normal battery is 4 to 6 hours. So actually progressing that technology is going to be huge. And then hydrogen, again, is potentially a source of energy storage as well. But again, converting that back into energy is costly.
So it's the cost element.
Absolutely, yeah.
What about the...
It's definitely doable. The technology exists, and it is improving. Will it improve fast enough to be rolled out? We don't know, but yeah, it's doable. It's obviously doable, and you have, as everyone said, like chemical storage exists, right? We used to have 6 weeks worth of coal just piled up waiting for an energy problem. We'll have some equivalent of that with hydrogen or ammonia or biofuel. Who knows? Like there's lots of ways to do it. It's a solvable problem.
But what about the cost of it?
It will cost, and the cost will vary, right? Like if you at the moment we have gas plants that are turned on once a year when there's peak loading. That's sat there not doing anything 364 days a year. That costs a lot, but we know how to tolerate that cost. We're just going to have to get used to a different economic balance.
Yeah. Why?
My personal view is I think we should store CO2 and electricity as a form of format, one carbon molecule, but it can be used by many different organisms to make different products. Format can be stored quickly by inorganic way. So basically you can use a simple electrode and pump in CO2. Quickly this format can be formed with high rate. So that's my view. So, and also I talked with some industry people. They talk about the huge amount, tons of this CO2, how be quickly. Biological system is very good in one hand, but it's slow. To quickly take in this CO2 is slower. But this inorganic electrode can quickly convert CO2 into formate, and then in a biological system can use this formate and convert that into highly valuable products. That's my view. Yeah, the combination.
Yeah, I'm just aware from a policy perspective, the UK are pretty bad at this long-term energy storage, and it's, you know, how do we, and I've never really understood what the cost implications are. Anyway, there's questions for me. There's many questions. Let's take one at the back first. No, come forward first, that's it. Okay.
Hi everyone, great set of talks, really enjoyed it. So me, I'm Chet Ladd, I'm matricked 1995 from Teddy Hall, so alumnus in biochemistry. And also what do I do now? I'm head of strategy for E.ON UK, so in the energy industry. But my question is for Wei, because the technology you talked about today has made me the most optimistic that I've been for a very long time, so in terms of the potential for the technology. So I'd just like to know more about your path to commercialization. Sort of when do you think it's possible to scale?
Okay. Actually, Teddy Hall Fellow in Thompson and I, we are working on this now together, trying to commercialize these things. I think I'm quite optimistic because some people talk to me, industry people. For example, that's one industry, they release 1 billion tons CO2 each year. And they seriously they either bury this CO2 or they want to make good use of this CO2, convert that into useful products. So that's why we can do this. Fundamentally, as I say, because we are working on science, fundamentally, if you want to quickly convert CO2, you just have two things. One is energy transfer efficiency. Secondly is mass transfer efficiency. So energy transfer efficiency, we just talk about that. We may, because rhodopsin is complementary to existing chlorophyll system, maybe even coexist with a microalgae together to maximize energy harvesting. So for the energy, for mass transfer efficiency, actually Kathy just asked that important question, how to quickly convert CO2 into something. So I think, in my view, we can do two steps. Convert CO2 into formate in quick way, using inorganic electrode system quickly. We can produce that large amount as well. And this formate can be used as a precursor to make a food, sugar, products, fine chemicals, all these things. I think this is the route. It's a hybrid system. That's my personal view.
Fantastic. Steve.
So, yeah, I'm Steve Smith. I'm a fellow here at Teddy Hall and a director of Oxford Net Zero, so particularly interested in all your talks, and I learned a lot. A question for any or all of you about refineries. So refineries are the bottlenecks through which our current sort of liquid and gaseous fossil fuel system goes through to make plastics as well as fuels. I was struck that at least two of you, Professor Wei and John, talk about methods that will involve refineries to make a product at the end. And also they're incredibly large structures that last a long time, involve a lot of finance, and they're all kind of built a little bit bespoke to deal with different fractions. So what do you see as the future path for refineries in a world where we're going to be using a lot less fossil fuels, but maybe using different chemicals and wanting different chemicals? Are they a hindrance or a help in this transition?
So let's start, first of all, at this end.
Yeah, so my oil and gas background comes in here. I've seen refineries and they're hugely complex, and in terms of the configuration, hugely complex. What we're seeing now, and I didn't mention talk about it that much, but I also work in the biofuel space. We're seeing biofuels being tested by different refineries. So I wouldn't say, I actually would think of it as a positive, because if we are using fewer fossil fuels, these refineries otherwise would be stranded assets. They would be defunct. So the fact that we've got more biofuels coming through and potential, use of sustainable aviation fuels, I think is actually positive. It extends their lifetime. And the other thing that we did it when I was in ADNOC, a lot of these refineries are being converted into petrochemicals, petrochemical plants. And the demand for plastics and all those petrochemicals is actually not decreasing. So I don't think refineries are going anywhere too quickly. I think they're here to stay. But it's how we adapt them.
They'll change, they'll evolve over time. New ones are built, old ones will shut, and you'll see a change, but it's going to take decades. They'll be with us for a long time. Yeah, agree.
In my view, in the ideal world, is we keep current infrastructure, but change the input.
Yeah.
We instead of using fossil fuel, we can use a CO2, plant tissue, waste plastic, and water as input, but keep current infrastructure, but using a sustainable way to transform this into some traditional chemical we normally use. I think this is the view. I think recently Nature also mentioned that. So this is the future. So you don't want to dismantle all this infrastructure. You can keep that, but you use a biorefinery system. So that's the future.
Did you want to add anything to this? Okay, next question. Let's have Dimitri, and then we'll have Tony. Dimitri.
Hi, I am a fellow in this college and a professor of financial economics, and I would like to ask more of an economics kind of question. Besides the costing of all of these technologies and scalability increasing in terms of scale, one might need to consider the second-order effects and the externalities that the adoption of this energy produces. In particular, the cross-border regulatory arbitrage, where basically you transfer the externality away from us that we're doing well, it seems, according to this plot, and even more importantly, the distributional consequences of adopting emerging new technologies and so on and so forth, and what trade-offs one should consider in order to be able to push the net zero agenda and the transition risk that results.
Would like to have a go at that, would you? Yes, Tina.
Well, if I understood what you're asking, it's partly about who bears the costs of the energy transition. Is that part of what you're thinking about? So is it sort of within society who's paying if there are additional costs to moving to low carbon technologies or low carbon sort of electricity supply systems? How are we ensuring that the sort of heaviest burdens falls on the broadest shoulders, if that's what we want to do, or ensuring that everybody benefits from the energy transition? And I think to some extent that's a live issue in the UK at the moment. So our current government has got as one of its pledges that is going to reduce people's energy bills. And we've just seen something happen in the budget where they've taken some policy costs off electricity bills and put them into general taxation. And they've also removed a piece of policy that was an energy company obligation scheme that's been in UK policy for at least 25 years. Seems to have gone, and that has been sort of supporting lower income households to reduce, sort of have improved households, improved homes, lower energy bills and so on. So there is a lot of concern about who's paying and who's going to pay for the expanded electricity networks that we need. Well, sort of us, but how are us paying for it? Is it through our bills or is it through general taxation or some mix of that? And I think that's where a lot of the distributional discussions are around at the moment. Because lower income households pay a lot more percentage of their income on energy costs than higher income households. So if you put all the costs onto energy bills, of course, that's sort of got a higher impact on low income households. So I think I'm not really answering your question. I'm just telling you how I understand it's part of the problem.
Do you want to add to this?
I think the second order effects were partly what I was trying to touch on in my presentation, and the point being it has to be a global effort. And we talk often about our UK emissions or European emissions. I don't think that narrative really holds true. When we have these COPs, we just had COP30 in Brazil. The whole point is to discuss them, but we're so interrelated. And we talk about UK energy security, especially in the light of Ukraine and having domestic security. But with these new technologies, it's very difficult to remain independent from an energy perspective because we're so interrelated. And the way that we're moving with renewable technologies, like I said, with the minerals and the processing, maybe that's what's going to drive nuclear. So it's a really complex, and it has to be globally orchestrated. Yeah.
Okay. Do you want to add to this, or I'll go to the next question?
Yeah, there's one point I want to make, which is we talk a lot about subsidies for green technologies, and those are definitely needed, and the hope is that those subsidies reduce over time. But the thing that is often sometimes stated but often forgotten. Fossil fuels are heavily subsidised.
Yeah.
You know, there are millions of dollars. I think there's a report a few years ago from the UN, which is like it's $1 million a minute go to global fossil fuel companies, both in terms of direct tax giveaways, but also just they're allowed to use the air as a sewer. You know, they're allowed to put CO2 in, and there's no externalities there. So yes, we should always try and price in externalities. Capitalism doesn't work if you don't price in externalities, and maybe we have to look actually at the current technology rather than new ones before we look at them first.
Okay,
yeah.
Thank you. Tony.
Hello, name's Tony Doyle. I'm a research scientist. You mentioned about storage of energy, and I was also intrigued to hear that the cost of green hydrogen is twice that of producing it from fossil fuels. I think we are paying some wind generating plants to stop producing energy when we have surplus because we don't have the grid. But it does seem to me that instead of doing that, we could accept that surplus energy for free, electrolyse water, keep it in old-fashioned gasometers. I don't know whether anyone remembers gasometers. Have those gasometers on the sites of gas-fired generators, convert power stations, convert those power stations to burn the hydrogen, and you've got virtually free green hydrogen. You've got the wires already going to and from those gas-fired power stations, and so you would have a sustainable use of surplus wind energy or solar energy, and then a good storage system.
So let me put that question to you. Does that? Okay. What's the question, Tony? I mean, I think it's fantastic. What's any views on that?
I mean, I agree. I mean, in theory, it works. In practice, I mean, I was at a conference yesterday on national policy and regional collaboration in hydrogen, and again, this is now UK specific. We have NESO that's just been created by the government, so the National Energy Systems Operator, for the first time looking at the energy system as a whole in the UK. Hopefully things like that will help, because we need to understand how hydrogen is going to sit alongside wind and solar and the existing grid and natural gas. So, yeah.
I want to come in on that because again, we work on a direct hydrogen competitor, and I think the big problem with that theory is you have to then build a hydrogen electrolyser that is sat there doing nothing 90% of the time. These things are not facilities built to sit idle 90% of the time and just ramp up, ramp down. It's a massive waste of resources to put all that steel, cement, manpower stuff in the ground to convert hydrogen or to convert water into hydrogen occasionally, only to convert it back. It's actually not as efficient when you look at it from a systems perspective. And also, I'm telling you, storing hydrogen like that is not, you can't use gas facilities to reuse hydrogen. Those are going to have to be rebuilt as well. It's not a one-to-one. And I think that's maybe a bit of the hydrogen hype. We could do this with hydrogen. As I said, 100 million tons of hydrogen is needed for fertilizers alone. The cost of fertilizers is double. The cost of green hydrogen's four times fossil, I think, 4 or 5 times. So it's a big unsolved thing, and I don't actually think that's a good step for the grid or for the country.
Okay.
Yeah.
Other questions? We've got Richard right at the back. Richard.
Hello. Thank you for lovely talks. I'm Richard Wilden, Professor of Offshore Renewable Energy and a different fellow in the college. Can I ask you to comment on the unintended consequences of well-meaning government policies in your respective areas and how we might mitigate against them? I guess what I'm driving at, and some of you touched on this, is we have this habit of putting policies in place and then without putting the mechanisms in place to support them, and you end up with virgin palm oil. You end up with being used as a recycled product, and we do the same thing with plastics, etc. So if you could comment in your respective areas, that'd be quite interesting.
So let's start with unintended consequences.
I suppose in my example, I was trying to be positive about policy packages. If you design them correctly and thoughtfully, and you keep evaluating them and you keep checking whether they're working, you can actually get a really good result without unintended consequences. But of course, that's we know that's not always the case. And so there was a National Audit Office report just a couple of weeks ago about a a policy to do solid wall insulation in homes that has, because of poor workmanship largely, has led to problems with mould and damp in homes. Now that's, in a way, that's not, actually contradicting myself, that's not really an unintended consequence. That's a poorly managed system where quality is not taken account of and probably costs are screwed down too tight. So, in theory, we know how to do good policy making, we know how to do consultation, we know how to get technical experts on board, we know how to do evaluation and keep going around that loop to make sure that things work. But maybe what you're thinking about is kind of going beyond the system we're looking at and things that happen outside of that system. And that's, perhaps I'll let one of my colleagues sort of talk about that.
Down the line then.
Again, I can talk about hydrogen because I know the hydrogen policy quite well, and there's many unintended consequences of the government policy on that. And, we talked about subsidies and the cost of hydrogen, and so subsidies are going to be a big part of it. And we've got these HAR rounds, hydrogen allocation rounds, that the government has instituted. We've had HAR1, we've got HAR2 shortlisted as well. So these were projects that were selected across the country, hydrogen projects, green hydrogen projects, that were being subsidised and given grants and something called the contract for difference, which is to reduce the difference between blue hydrogen and green hydrogen. All great ideas and hugely supportive, but in practice, what it's meant is it's been very stop-start. It hasn't been. It's actually the capacity of hydrogen that it's targeting is only a tenth of actually what we'll need. So we're in this sort of vicious cycle that we can't scale up because it's supporting smaller projects. Because we can't scale up, we can't get to that critical inflection point to reduce the costs. So we're stuck in this bit of a hamster wheel. And we have teams waiting for HAR2 negotiations, but they've been delayed. The hydrogen strategy was supposed to be issued 2 weeks ago, but it hasn't. So it puts the whole industry in this very sort of paralytic situation. We want to move forward, but we can't. So I guess if that answers your question, there's
unintended consequences.
Yeah, I actually want to go back to the used cooking oil, virgin cooking oil, because a couple of people mentioned it. I actually don't view it as a bad thing per se that used cooking oil is more expensive than virgin. The reason it's more expensive is because there's a use for it. The alternative to using it in fuel is just incinerating it. And that's definitely not good because then you're releasing all those emissions anyway. So it's actually a good thing that happens, and that requires collection, distribution, processing. That's where that cost comes from. So obviously, it sounds silly, and I think it's more the point that a waste isn't free. Wastes aren't free. As soon as you put steel in the ground, it's no longer a waste. It's a product. And the second thing, actually, there's lots of problems with policy, but I think the thing the government can do, and our government is kind of good at, kind of bad at sometimes, is just certainty and speed. So within the SAF world, there's these mandates that we have to burn 2% SAF, or 2% of the fuel barrel has to be SAF this year. It's got to be 12% by 2030. That's a massive scale up. Good that that's in place. That now means everyone can move, people can put money into facilities. That has stimulated a huge amount of investment to get it done. But there's a second piece to that, which is what happens if you don't do it. There's got to be teeth to that mechanism, and there's the revenue certainty mechanism was meant to be this thing that punishes airlines for not meeting those targets. So we've got the targets, but we actually don't yet have the revenue certainty mechanism to punish them. So will it be enforced? Will both be dropped? So there's that lack of certainty, means again investment sort of goes, oh no, we'll wait and see what happens. So moving with certainty and speed is the most important thing. And I actually, governments get a kick a lot of the time. I don't think they've been too bad at that. They can definitely do better, but there's green shoots.
Unintended consequence. I think at the beginning, we should implement the life cycle analysis. You need to think about the whole things from your raw material to the final material, and then recycle back. And the whole, you cannot just only look at one point. You need to think about after many years, how to dispose this waste. Or, for example, for biological process, would you generate any waste? And how do you use this waste? So basically implement this life cycle analysis is I think we should consider that.
Thank you. Other questions? There's one over here on the side with a red jacket on.
Hi, I'm Callum Byram, and forgive me, I don't have any official affiliations with Teddy Hall. I have worked for most of my career in energy, though, firstly in fusion and currently in renewables. So a slightly controversial question here. Is the root of the problem ultimately that energy is too cheap and this has led to vast amounts of wastage and little innovation? And if so, what do we do about it?
Who's going to take that one? Maybe.
Is energy too cheap? Well, I'm just going to talk out loud because that's deep. I guess the cheap energy has fueled the industrial revolution, right? It's fueled our progress and the growth in our economies. So, and as I talked about, we need more of it. So, but your point is cheap energy incentivizing the right behaviours? And I think that's the point. And here we have this dichotomy about AI is going to solve everything, and so let's put everything into AI, but it requires so much energy. But is it? So, you know, there's probably an economic model for it somewhere, but I see your point, yeah.
I thought your AI comment earlier was shocking. Yeah. I have to say, I think, yes, I think most people in the room probably didn't quite realise that. But, Ian, just a microphone here. Oh.
Hi, I'm Ian Thompson, one of the fellows there, and also part of engineering. I just want to pick on the issue that the subsidies that go into hydrocarbons at the moment, which is kind of generally ignored. You highlighted it, but it's not often mentioned. I mean, one of the problems is if we could use some of that subsidies to actually explore other technologies and also give those other technologies an opportunity to sort of develop. You know, we quickly dismiss things and say, well, that's not going to work. I mean, one of the areas that we've been interested in for years, and actually comes from the time I worked in Shell, was that we could never work out why, well, we're beginning to work out why a cow is about 30 times more efficient at converting grass into methane, you know? And if we could harness that, then you could reduce the size of anaerobic digesters and they can become economical. If you try to raise money to do something like that, or it takes a bit of time, we kind of know what it is. It isn't the cow, it's the microbes in the cow and a combination of both. But a part of it is funding. You know, something like that seemed to be eccentric. But a cow is doing it. You know, can we mimic it? If we can mimic it, then the footprint of anaerobic digesters becomes much smaller, and then it becomes feasible and economic.
So what's your question?
The question is, well, is a mechanism whereby you can allow technologies to mature. I mean, that's...
So, yeah,
I'm happy to take that first. Okay. Do you want to go? Go ahead, John.
Two answers. Yeah.
Okay. It's not quite a direct answer to that question, but I think it's all worth saying. It's like I work in clean tech. I speak to investors way too much, and they're really keen. People are really keen to put their money in green technologies, but they also have to look at returns. And I think there's often numbers like, oh, the clean tech sector has raised this much money, blah 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 blah. It's often not segmented by what that money actually goes to. And when you look at it, the vast majority of clean tech funding or revenue and all this, it goes into carbon accounting or it goes into carbon credit, like accreditation companies. Only a small fraction of it, I think it's less than maybe, I'm going to eyeball it, 20%, goes on deep tech, hardware stuff to actually decarbonize. There's so much potential profit to be made in just like swapping these credits around, working out, oh, you've emitted this much or not. That has actually got most of the funding. A lot of the big companies within the clean tech space actually aren't doing hardware. They're doing like, you know, digital services have something to add, but like that's on top of physical infrastructure. And I think you're completely right that maybe we're misaligning investment into some of these sectors.
Yeah, I actually had a slide in my presentation, which I took out last minute, Ray, which is exactly this point about venture capital and funding new technologies. And, you know, at the moment we have, you know, UK government grants, R&D grants, but when it actually comes to new technologies, you actually need patient capital. And again, it's an oxymoron because capital isn't patient, right? We have shareholders that are expecting returns. So with new technologies, and I work with startups as well, and we've gone through fundraising rounds, it can often take 2, 3, 4, 5 years to get the we talk about commercialization way of view, you know, to actually get the funding, because these things work in the labs, right? And we prove them in labs. We have so many university spin-outs. When you get to scale up and commercialization and the real world, and you put algae outside when there's windy and it's hot and it's rainy and there's pests and there's viruses, it doesn't look as great as it does in the lab. So you need patient capital that's going to stay with you and have faith in you, and that takes 4 or 5 years. And for a startup to actually break even, it can be 5, 6, 7, 8 years down the line. So we have venture capital funds, but again, and then AI comes and robotics comes, and suddenly their attention is diverted. So
certainly, there's one of the other problems is procurement. I mean, if the UK government in particular were to procure actually and put their money behind the sort of buying of some of these products, if they've got that target for sustainable aviation fuel, well, let's buy it from companies that are actually making it now. And I think that's another problem that comes time and again. Okay, other questions? There's several. There's one at the back. Yes, he's here.
Good evening, thank you. And Andrew Hagen. So I was, like Chet, a 1994 alumnus here in chemistry. I was also an advisor to the Smith School of Enterprise and the Environment here in Oxford. And then I've worked for about the last 20 years in this area in various forms, 10 years at the World Economic Forum, looking at a lot of these projects, or doing big projects on some of the subjects that are being discussed. I would say one or two things. I mean, definitely go away and read about this, because you're getting the tip of the iceberg here tonight. We're not going into depth on any of the subjects, and a lot of things really do need a lot of reading around. My question is going to be around the public and societal narrative. I'll come back to it, just one or two things. I mean, a lot of things that I would love to sit and discuss and dispute, but one or two that can't slip away. I mean, the figures, some of them are under-exaggerated. So Madiha and Kathy, you were worried about the AI figure. It's vastly understated.
But let's have the question now, because we've got lots of other questions. So
sure, the question's going to be around the public narrative. I mean, there's so many other things to come back to, but bringing the public along. I mean, the government has to get voted in. I mean, we're living in a market economy. We have to get industry involved and brought along as well and tailor to the end markets. But in terms of public policy, bringing the public along is essential. And we're not going into some of the factors that really got me working on this in a hard way, like the Stern report, which shows that, spend money now saves you a lot of money in the future. We're not outlining that to the public. We're just letting them think that we can go on business as usual.
So how do we change the public narrative, I think, is the question that we're... It's quite short answers because we've got many other hands.
Okay. Well, I think one of the... I mean, rather disappointingly in the UK, until recently, we had a sort of political consensus around net zero, right? All the main parties were in favour of it. Unfortunately, the Conservative Party are now less in favour than they used to be, and we know reform as pretty anti, and that's really disappointing. So there's that kind of public discourse is not as unified as it was, although if you look at a lot of public opinion polls on what the public want and whether they support net zero, there's very little climate scepticism out there, and there's a lot of support for net zero policies, even when you tell people what that actually means. So I think one way of sort of encouraging people is to show people the real benefits to them in their real lives. People probably don't know that they're using less energy than they were 20 years ago. They might not, but that's a real benefit from public policy, that on average everybody's using 20% less energy in their homes or whatever it is. They've got access to cars that use a lot less energy than they used to. So showing the benefits, showing those benefits can be for everybody. And talking about, if we want to think about energy security, if you're generating most of your energy from renewables in Britain, then you're not dependent on international gas markets, which is what's making our energy prices so high. So I think there are a lot of positive narratives that we can use to help people come along that include energy justice, that include, good green jobs and all those positive things that will speak to people, as well as the environmental benefits.
Okay, unless we're burning, I think we've got a couple more questions. So I think let's ask. We must stop at 1:45. I think it's only fair on our speakers. There are drinks as well, and carry the questions on. But let's take one from Tracy.
Hi, great. I'm Professor Tracy Berry, and I'm an old girl from Teddy Hall, same year as Chet, 1995. So I have a comment about the AI question. So AI, yes, it is using lots of energy now, but I guess when quantum computers come in, I think it won't be so energy intensive, so that's something to think about. And my comment is, I'm not in energy. I'm a particle physicist, so I use lots of energy. What about carbon offsetting? I go to conferences and they say, oh, well, we're going to use all this bad energy, but we're going to carbon offset. I mean, is your opinion that's just kind of, going around it and as a way to kind of avoid the real problem? What's your view on that?
So the question is carbon offsetting.
Yeah,
so would you like to take it?
Sorry, I think it's the final word on this is greenwashing, and I think that's the danger, is that not all carbon offsetting is greenwashing, but like it's so easy to get there. Again, that's why there's all these companies that are in carbon accreditation and carbon trading, because there's money to be made by doing it, and you just don't know. And say we invest heavily in carbon offsetting, or even sort of slightly more new, which is the geological engineering, putting stuff up in the sky that's going to help reflect sunlight. 5 years' time, 10 years' time, you find out it's not working the way you thought it does. That happens all the time with technology. It's a big risk to put everything on that. Yeah.
Wade, do you want to add to that?
Just quick, I think at the moment we are not just have a carbon neutral. We need to minus carbon. We need to use take a lot of carbon dioxide from the atmosphere. I think that's the way. I think it's not only single technology can to solve this big problem. Maybe it's multiple technology, including some biotechnology and also geotechnology to bury these things, or other technology combination together. I think we need the coordination of these technologies together.
Okay, we've got time for probably 2 more questions. Got one here and then one at the front.
Hi, I'm Mike Franklin, and I'm a retired neuroscientist, so a long way from this, ex-Teddy Hall. I just want to ask a very basic question. I'm sort of worried and a bit depressed about some of the stuff I've heard tonight, but you've really told us about our energy demands going up and up and up and getting beyond scale. My question to the whole panel is, can all you new energy makers ever catch up with the curve?
Very good question. Right, let's start at the other end. Why?
Nuclear energy. Sorry. Can you repeat your? Oh, global. I think solar energy, in my view, is the ultimate solution to solve the energy issue. So
you will also solar will be able to catch up with the increasing energy demand. Is that your?
Yes. Yeah. That's my personal view. Yeah.
Just a small addition is that I don't think we need to completely catch up. I think often we get obsessed with, aviation is a hard to abate sector, but it's 2%. You can actually do the first 50% quite easily, and solar, wind, batteries can actually take that out. I think that's the real positive. We can buy extra time for the really weird technologies and innovations to come along just by doing the easy things, which is solar. To be honest, like solar panels, they answer a lot of problems. It's not as bad as it looks.
Yes, I would agree with that, and I think what I was trying to demonstrate in my presentation is we have a lot of private capital going towards energy efficiency because it's so imperative for this next generation of development and digital development. So I think we're getting capital flows in that area, and Amazon and Facebook and Microsoft investing in those areas is going to help all of us, right? That they're investing in these new and more efficient technologies that's actually going to help everybody, not just their technology companies. So I am hopeful.
And I would just slightly challenge your narrative that energy use is up. In the rich world, actually it isn't. It's flat or it's going down already. And we need to think about demand as well as supply. There's lots of ways of meeting human needs without using more and more energy, and we need to focus on that as well as the smart new ways of supplying green energy.
Right, we are going to stop now. There's plenty of opportunity to ask our speakers questions. I do have one more question because I want to finish on a positive note, and I think we have heard some very positive things. And for each of you, what gives you hope about a truly sustainable energy future? Bye.
Energy future, that's a very big question. So, okay, if you look at maybe repeat that thing. If you look at the ultimate energy for the human, I think if we want to build our civilization, inevitably we need more energy because from this disorder system to other things, we need consume energy. But the solar energy is ultimate energy. Actually, wind and hydraulic energy is indirect from solar, right? So actually, solar energy is the ultimate source. So we need to think about that and make use of solar energy more efficiently. That's maybe my point.
Yeah, it's sometimes hard talking to other founders in the space. It can be really depressing, particularly when you're talking to investors that are saying no. But to be honest, if you look at over the last couple of years, there's been some depressing news. But if you look at over 10, 15, 20, 30 years, everyone has now woken up to where the climate activists were in the 80s. Everyone now knows climate change is real. And I think that if you take just a little step back and look at over a wider range, we are going in the right direction. Donald Trump and all these people can try and they can say drill, baby, drill and all this kind of stuff, but that doesn't make it any more profitable to dig coal out of the ground and burn it. There's no new coal plants in the US, even though he said he wanted it. So you can't fight the tide.
Yeah, I echo that. And I work with a number of founders, biofuels, battery energy storage, new technologies. There's always new technologies. So that gives me hope. The other thing that gives me hope, I lived in the Middle East for 6 years. You know, everyone thinks oil and gas. They're investing more in renewables than many other countries. So, you know, that wasn't happening 10, 15 years ago. So there's absolutely a change. Yeah.
What?
Well, I mean, I think fridges are the future. Now, I mean, I think, you know, we've got a lot of the technologies we already need. We're inventing some cool new stuff, which is great. And what we're also starting to get is ways of including people in making decisions that are right for society. So I think we've got a lot of the key technologies. Now we need to work out how to organise ourselves so that we can all have the energy that we need and we can, you know, make the world a better place.
Right, on that note, we are going to stop. I just want to say a huge thank you to all four speakers for really giving us new thoughts, new ways of thinking of these things, and also allowing us to end on an upbeat note. So thank you very, very much. I also just want to say a very quick thank you to Maxine and to Claire and to Andrea at the back, who've been the ones who are really coordinating this, and also to the people who've been doing the sound, which has been fantastic. So thank you very much. Please come and have a drink, come and speak to our speakers this evening, and come again next time. Thank you.